This talk is part of an online undergraduate course on complex analysis and is where we finally start talking about complex integration. So in real analysis, we can integrate from a to b some real valued function f of x dx, at least if f is continuous or well behaved. And we want to find an analogue of this for complex variables, so we might want to define an integral from complex numbers a to b of some complex function f of z with respect to a complex variable z. So here z, a, b and f are all complex. The function f is usually holomorphic. It doesn't have to be holomorphic, but if f isn't holomorphic, then this integral turns out to be not particularly useful. Well, there's one obvious problem in generalizing from real integrals to complex integrals. So in real integrals, we're integrating from a point A to a point B, and as we go from A to B, we sort of add up values of the function f at that point. Now, if we're doing complex integration, we might have a point A in the complex plane and a point B in the complex plane. So this is I, this is 1, and so on. And we want to integrate from A to B and add up values of f between A and B. And the trouble is there are lots of different paths between A and B. So we could go like that, or like that, or like that. And in general, even if f is holomorphic, the value of the integral from A to B will depend on which path we take from A to B. So we can't really define the integral from A to B of a complex function. What we have to do instead is define the integral along a path c from A to B. So c might be a path here. So c is a path from A to B of f of z dz. So that's the first change we need to make for complex integrals. We need to integrate along paths rather than just integrate between 2 points. There's one easy case when we can do this complex integral, which is when a and b are real numbers and the path goes along them along the real axis. And then all we need to do is to write f as a sum of real and imaginary parts. So we write f is equal to g plus I times h. And rather obviously we define the integral from a to b of f dx to be the integral from a to b of g dx plus I times the integral of a to b of h dx. So we can just make it complex linear. Well, so that does the case of complex integrals of a path along the real line, but obviously we want to define a more general integral along a path in the complex plane. And to do this, we need to start by recalling how we define a real integral. So let's recall the definition of a to b of f of x dx, where let's just take f to be continuous for simplicity, and a and b to be finite. And the key point here is that an integral is really a sum. Well, actually, it's not quite a sum. Strictly speaking, it's a limit of a sum. And I'm going to write a limit of, in this very pale yellow ink that's almost impossible to read. And the reason for that is I don't actually want you to read this. I sort of want you to forget about the limit bit for a moment because it's not terribly important. So you should think of an integral as being a sum. So let's compare them. So if we've got a sum from n to a of b of f of n, we write it like this, and we write the integral from a to b of f of x dx like this. And first of all, we note that notation is very similar. So this is an s. Well, it's a Greek s, which is a sigma. And this integral sign is also an s. The integral sign started off as an s standing for sum and kind of got stretched out for some reason I've never quite figured out. So really these two expressions are almost identical. The only difference is we've got this dx here, but what we should really do is have a times 1 here, only for rather obvious reasons, people don't bother putting in times 1 there. So let's draw pictures of these to see what the comparison is. So for the integral, what we're doing is we're taking the points a plus 1, and so on up to b, and we can sort of draw rectangles of size f of so the rectangles have width 1, which is this bit here, and they have height given by f of n, which is this bit here. So this is just the sum of the areas of these rectangles. And we recall the integral is very similar, except instead of taking all these rectangles of width 1, we pick a lot of points very close together. Let's call them x0, x1, x2, and so on. And we take a lot of very thin rectangles. And dx is going to be short for xi plus 1 minus xi. It means the difference of the x's, in other words, the difference of these two. So each rectangle has height f of x and width dx. So this term here is just the area of each rectangle. And what this integral really is, it's just a sum over f of xn over xn plus 1 minus xn, where this bit is, of course, just dx. And as I said, it's not quite a sum because we should take a limit, and I'm putting the limit in very faint ink so you don't pay too much attention to it. So that's the definition of an integral for real functions. It's really just the limit of a sum. And we're going to define it for complex integrals in much the same way. So now what we do is we want to take a path from A to B, and just as we divided up the interval into lots of little bits, we're going to divide this path up into little bits. So I'll call these points z0, z1, z2, and so on, up to zn. And now the integral over this path c of f of z dz is just going to be given by a sum. We take f of zi, and now we take the difference of the zi's, which is just ci plus 1 minus ci, just as before. And of course, we should really take a limit of this as the number of points tends to infinity and the distance between them tends to 0. So this bit here is just, think of this as being just dzi. We can ask, what is this path exactly? Well, the path is going to be a function from some real interval in the real numbers to the complex numbers. So we can think of this as being a function p, or possibly rho if you prefer, with p of r is equal to a and p of s is equal to b, and so on. So a path is just a way of is really just a function from an interval to the complex numbers. Now, when we can ask, when does the limit exist? Well, the limit exists if, first of all, f is continuous, and secondly, the path c has finite length. Well, I better define what the length of a path is. We just sort of define it in the obvious way. So here the length is going to be the supremum of z1 minus z0 plus, let's take the absolute value, plus z2 minus z1, and so on. So geometrically what's going on here is if we've got a path like this with points z0, z1, z2, and z3, then we take the length of all the straight line segments between these points. So this is the absolute value of z1 minus z0, and this is the absolute value of z2 minus z1, and so on. So this sum here is the length of this orange path, and it's obvious that if you let the number of zi's tend to infinity and the distance between them tend to 0, then this sum will be a very reasonable approximation of the length of the path. In fact, we define the length of the path to be the supremum of this sum taken over all these decompositions. Now, we ought to prove the limit exists, but I'm not going to, because this is very similar to the proof that the real integral exists, so I'm going to skip it. The problem with this definition is it's not very easy to calculate. So the integral is given by this we take a rather complicated sum, and then we take a rather complicated looking limit of this rather complicated looking sum, and it's very difficult to use this directly to calculate integrals. So I'm going to mention two other equivalent ways of defining the integral over c of f of z dz. So you recall that c is given by a function rho from Rs to c, and now assume that rho or p has a continuous derivative as a complex valued function. So we're putting z is equal to rho of x, and now in this integral the formula for change of variables for this sort of integral works just as it does for real integrals, and the proof is much the same. So I'm going to change variables by putting dz equals the derivative of p with respect to x times dx. So what we're just saying is that zi plus 1 minus ci is approximately equal to p dash of x times xi plus 1 minus xi. And as the number of z's and the number of x's increases, this limit gets sufficiently good that we can make this change of variable. So this integral here now becomes the integral from r to s of f of p of x times p dash of x dx. So this bit here is just dz, and this bit here is just z, and we've had to make the obvious change of path from, we're now integrating over the interval from r to s. And now this is just a function where we integrate along the real axis, which we can do just by splitting into real and imaginary parts. So if you want, you can use this as an alternative definition. I don't like using it as the fundamental definition because it's not at all clear where this expression comes from if you just write it down. I mean, you know, why are we putting the derivative of the path in here? Well, the reason why we put the derivative in there is this is just another way of writing the integral, which was correctly defined as being a sort of sum, or rather a limit of a sum. I should point out that quite often the path that we take doesn't have a continuous derivative. We might want to integrate along a path that looks something like this, but that's not a big deal because we can split this up into a finite number of pieces, each of which has a continuous derivative, so we can just define the integral, the sum of the integrals over these pieces. There's another definition of the complex integral, which you can just reduce it to a path integral that you get in multivariable calculus. So we can just define the integral over c of f of z dz. Well, here we just write f is equal to u plus iv, and we want to write this as the integral of u plus iv, and z is equal to x plus iy, dx plus I dy. And now we can just write this as the usual sort of path integral you get in vector calculus. So it's the integral over c of u dx minus v dy, so that's a perfectly good path integral, plus I times the integral over c of v dx plus u dy. So this gives a third way of defining the complex integral in terms of path integrals in vector calculus. Of course, this isn't really any different from the other definitions, because if you look at the definition of the path integral in vector calculus, you find this just reduces to one of the two previous definitions we gave. So the next thing to notice is that the integral over a path of f of z dz is almost independent of the parameterization rho going from Rs to C. So if we get a different function rho, say P, if we find a different P, say P1 from Rs to C with the same image, then we still get the same integral. And the reason for that is this integral is approximated by sums of the form f of zi times zi plus 1 minus zi. And these sums are independent of the parameterization of the path. You just have to choose points zi that are actually on the path. Well, I said almost independent. There's one way in which it does depend. We need to pay attention to the direction of the path C. So we could take a map P going from RS to C, taking P of R to A and P of S to B, but we could also reverse direction and take P of R to B and P of S to A and go back in the other direction. And what this does is it changes the sign. And that's pretty obvious because you just notice that the sign of this bit gets changed. And this is kind of like saying in real analysis the integral from A to B of something is equal to minus the integral from B to A of something. So most of the time all that matters is the image of this path C and the direction you go along this image in. There are some basic properties of integrals that are very much like real integrals. For example, the integral over C1 plus, of fc dz plus the integral over C2 of fc dz is the integral over C1 union C2 of fc dz. Here C1 might look like this and C2 might look like this. And it's kind of almost obvious from the definition that if you combine two paths, you just get the sum of the integrals. The integral is also additive. The integral over c of f plus g dz is the integral of f dz plus the integral of g dz. And again, this is kind of obvious because, for example, if you approximate the integral by a sum, all the sums are additive. So when you take limits, it's still additive. A slightly less obvious condition is that the integral over c of f of z dz has absolute value at most m times the length of c, where this is the length of c and m is an upper bound for the absolute value of f. And this follows because this is an upper bound for all the approximation sum of f of zi times zi plus 1 minus ci, because the sum of the absolute values of these is less than the length of the path by definition, and this term here is less than or equal to m. So we obtain a useful upper bound for any integral. It's at most the length of the path times an upper bound for the thing we're integrating. This is, of course, the complex analogue of the usual real estimate that the integral from a to b of f of x dx is less than or equal to m times b minus a, where m is an upper bound for f. Well, we should actually give an example of evaluating an integral explicitly. And in particular, what I want to do is to give an example to show that the integral can depend on the path from a to b. So what we're going to do is we're going to integrate z to the n dz over a path c, where c is a path from 1 to 1. Okay, well that looks a bit stupid. First of all, you could just take c to be given by p equals 1 everywhere. We could just take the constant path from 1 to 1, and then it's kind of pretty obvious that that would say the integral of z to the n dz is equal to 0, because all the numbers zi plus 1 minus ci are just equal to 0 in the sums approximating it. On the other hand, we can take a different path, and the path I'm going to take now starts at 1 and just goes round the origin counterclockwise. It's traditional in complex variables that whenever you go round something, you always go round counterclockwise. I have no idea why. But we need to write down this path explicitly, so I'm going to choose this parameterization. It goes from 0, the interval 0 to pi to the complex numbers, and it's just going to take point x to e to the ix. So you remember e to the ix is just a point on the unit circle with argument x. So as x goes from 0 to 2 pi, e to the ix will just go round this once. And then we can work out the integral over c of z to the n dz. Well, we need to know what z is. Well, z is equal to e to the ix, and dz is equal to I e to the ix. So this becomes the integral from 0 to 2 pi of e to the inx times I e to the ix dx, which is equal to I times the integral from 0 to 2 pi of e to the I times n plus 1 x dx. And this is equal to 0 most of the time if n is not equal to minus 1, because then we're just integrating some thing of the form e to the I times something x, and you can just write this as a sine of something x and a cosine of something x, and you know that sine and cosine have average value 0 over 0 to 2 pi. Well, if n is equal to minus 1, this becomes a constant, so it becomes a constant 1 in fact, so we get 2 pi I if n is equal to minus 1. So in particular, when n is equal to minus 1, we found two different paths from 1 to 1, such that the integral along these two paths is different. If you remember the lecture on harmonic functions, you remember things went wrong for harmonic functions when we went round a point where the function wasn't defined, and you were probably correctly suspecting that we've got the same problem here, because z to the minus 1 is not actually defined at this point inside the contour. What we're going to do next lecture is prove what is possibly the fundamental theorem of complex analysis called Cauchy's theorem, which says that the integral along a path doesn't depend very much on the path. In particular, if two paths are homotopic, meaning you can slide one into the other, then the integrals along these two paths of a holomorphic function are actually the same.